Yes, thank you. I hope you can see the slides. Yeah. So yes, the topic of my talk is quantitative thermography, and I want to start with a very old accident. In October 1875, a train wheel broke because the new but more brittle Bessemer steels were used instead of the old puddling steels, and this change of the material resulted in lots of failures. And although fatigue of metals had been known since 1842 from Victor Poncelet at the University of Metz in France, but the detailed investigation of August Röhler, published in 1877, marks the birth of modern materials testing. And 144 years later, the testing method is in principle still the same. And that's the main topic of my talk. If components are designed for applications with fatigue loads, then the fatigue strength is more important than the fatigue lifetime regime for most applications. To say clear, my car should be safe for infinite lifetime. But the fatigue strength regime suffers from the large scattering. You all know that, of cycles to failure and an overlaid scatter in the critical stress amplitude. So some materials have a fatigue limit of 2 million load cycles, some of 10 million load cycles, and FCC materials, no one really knows. It depends on the size of inclusions or the mechanical contrast between inclusions, maybe billions of load cycles. And for the fatigue strength, there are different methods present, such as the maximum likelihood method or the Hook method, and have been proposed and discussed, and they all have in common that at least 10 specimens are needed to get just the mean value of the fatigue strength. Up to 50 are needed for the scattering bands, and due to the large scattering, fatigue strength testing results in very high cost, and you all know that in high testing times, even with resonance testing systems. And just to point it out, the one specimen test for reliable fatigue strength is like the holy grail of fatigue testing. And for that goal, we want to use the heat generation inside the sample material, resulting in an increase in temperature to characterize the energy dissipation, and hence to get an idea of the internal processes that correlate with damage. This correlation of the dissipated energy, the mechanical hysteresis with temperature and damage, is very old. Even in the 1920s, there were already first attempts. But new technologies such as thermography or sensors with large resolutions opens up new possibilities. One base evaluation using thermography was done by Luong et al. They measured the temperature evolution in the middle of a sample in a stepwise load increase test, and they found if the stress axis is logarithmic, you can see on the left-hand side, the temperature evolution has a knee point, and this knee point can be correlated with the fatigue strength regime. But measuring just the temperature is not the right way, because if the temperature would lead to failure, then all samples would break in the middle of the parallel length. And we all know this is not the case. We need to measure the heat generation inside the sample during fatigue. And to be honest, if the glands are tempered, the temperature represents the heat generation. But if we go to the fatigue limit, the heat generation is quite small. You can see it here on the left-hand side. It's below 1 degree C. And if we want to know what happens at this point, we need a very, very good resolution. And below the knee point, the temperature increase is in the range of the resolution limit of infrared camera. And that's the challenge to deal with in this investigation. So standard techniques for thermometry use thermocouples or the infrared cameras, and the thermal resolution is about 0.1 degree C, a little bit better, for example, for lock-in thermography, but it does not reach the resolution of standard thermistors. And what we use in the studies are thermistors with negative temperature coefficients, so-called NTCs. And as you can see on the right-hand side, if the temperature increases about 20 degrees C, the electrical resistance changed from 12 kilo ohm to 6 kilo ohm. And that's the reason why we get this outstanding temperature resolution of about 1 microkelvin. But one big problem is that the NTCs are uncalibrated, and each sensor must be calibrated prior the evaluation in a water bath thermostat, but it can be reused after the tests. So if we now use these NTCs, we have a very low budget, but a very high effort method, because we need to measure the temperature at 3 distinct points on the sample along its parallel length. The idea is to measure the curvature of the temperature profile with just 3 sampling points, because the curvature characterizes the heat generation inside the material. So if we now consider just this simplified one-dimensional heat equation, and we assume that there is no heat exchange with the surroundings, so we have a good thermal isolation, that we measure a steady state, and we have no heat changes no heat from changes in the microstructure, and the thermal conductivity tensor is constant, and so on. We get the simple solution of this one-dimensional heat equation. It's just a parabola. And always in 1982, Klaus Stark proposed this method in his PhD thesis, but it was never published in English. We can get an idea of the shape of the parabola just from 3 distinct measurement points. So what we do now is we carry out a stepwise load increase test, and we measure the heat generated per load cycle from 3 NTCs. And what we do now is we pack our NTCs in a package of electro-isolation foil and double-sided sticky tape, put 3 sensors together, and use digital multimeters read out with LabVIEW to get the temperature profile of these small samples. So, and yeah, if we make this load increase test, we must ensure that we get a steady state of the temperature, as you can see here. To achieve a steady state of the temperature or the heat generated per load cycle is the blue curve. To get the steady state, we had to wait a couple of load cycles. In this study, it was not enough load cycles, so we have to increase the number of load cycles and the test becomes longer, but it is necessary to achieve the steady state for the further evaluation. We did this, and then we can contrast the heat generation to the step stress amplitude, and these curves here are gathered. Here you can see the results for aluminum cast alloy from selective laser melting, and of nanocrystalline and coarse grain nickel samples. And for the aluminum samples, there is no knee point visible. That means that the onset of plasticity leads to failure during less than 100,000 load cycles. This was the number of load cycles in one step. So we can calculate, we can evaluate the fatigue strength in only one easy load increase test, even without thermography. That's not surprising because it's a very brittle material. But if we consider the nickel samples, we can see that our nanocrystalline nickel from pulse electrodeposition is a very inhomogeneous material. We get very different results for the stress amplitude, and for the coarse grain material, we get a completely different level of the heat generated per load cycle at the knee point. So now we wanted to correlate this knee point with a standard evaluation for the fatigue strength, and we did this for low alloyed steel. And what we found is a very good good correlation. You can see here the value from a Hook evaluation, the maximum likelihood evaluation, and here the data from the thermometry, and you can see it correlates quite good. If we now consider a standard steel, we see that depending on the R ratio of the test, the stress amplitude at the knee point evolves as expected, and we can see an effect of the upper and lower yield point for the R 0.1 sample, resulting in a step in the Q curve at, a step here at the knee point. And this gives a clear evidence of the immediately starting dislocation mobility when the upper yield point is reached. So, and the knee point characterize a change in the cyclic hardening behavior. That's what the knee point tells us, and we can express a fit to both curves by the Morrow equation, and then we see that the knee point is simply a change in the coefficient of the cyclic hardening behavior. So if we now have a closer look to the heat equation, we can also allow for thermal convection effects, but the solution for the temperature profile becomes more complex. We must fit a double exponential solution to the profiles. And we did this using thermography as proposed by Guo et al. And they already did it in 2015. And they found also this knee point and a heat increase below the knee point, but their investigation suffered from the bad resolution of their infrared camera. Therefore, they could just measure high Q values. Q is the heat generated per load cycles of more than 50,000 joules per cubic meters. So we did the same. We used a micro epsilon TIM 160 camera with a thermal resolution of 40 millikelvin, and got surprisingly nearly the same results when we fitted the Stark parabola and the double exponential fit to the data, and we see just vanishing differences. So we concluded that the thermal convection effects are neglectable, and we can just use the simple parabolic fit for our further evaluations. In the last step, we did a simultaneously measurement with NTCs and with an infrared camera, of course, without the thermal isolation used for the NTCs. And we see the much better resolution of the NTCs in the fatigue strength regime, because 40 millikelvin thermal resolutions means that the limit for the heat generated per load cycle is around 1 kilojoule per square meter, per cubic meter. And that's not enough to resolve the behavior below the knee point. So I can conclude that choosing a method is a decision of time and costs for materials with low thermal conductivity and test setups with high frequencies. You can do the measurements with thermocouples or infrared cameras, although the infrared cameras are a little bit more expensive than thermocouples. But if the material has a high thermal conductivity, such as aluminum, and the temperature profile is flat and hence hard to measure, you need NTCs. Also, if the sample is small, then less heat is generated, and if you use a servo-hydraulic testing machine, less heat is produced per second, and this makes NTCs necessary to get good and reliable results even below this knee point. But one question remains: what is the link between this heat generated per load cycle at the knee point and damage? And this work by Stanzel-Czech showed that in the fatigue strength regime, there are several processes that influence the fatigue strength. The knee point is attributed to the onset of dislocation motion, but this is unfortunately not identical to damage. Therefore, we can assume that the knee point stress amplitude is just a lower estimate for cyclic dislocation motion and hence for the fatigue strength and not the fatigue strength level itself. So thank you very much for your attention.